my pleasure today to welcome Yuri Raman over here for our seminar series. Yuri graduated with a bachelor's from University of Pennsylvania, and later on worked with me in Jim Domestic's group in University of Wisconsin. So he is now the third person from that group that I've invited over here, I guess. So after that, he went to work with Mark Davis at Caltech, and a lot of his work has been in producing renewable chemicals as well as fuels from sugars and biosources. He has been extremely cryptic in his abstract today, but he says that he will cite specific examples, citing the role of catalytic pairs in enhancing the activation of targeted functional groups. So I'll let you explain that a little bit more and take it away. Yeah.
All right. Well, thank you very much, Hamid. And first of all, thank you for the invitation. It has been a dream of mine always to come here. You know, I think the EBI Center is a very famous worldwide center overall, you know, in the forefront of biomass conversion. And what I wanted to do today is share with you some of the results, you know, in a much smaller operation that we run at MIT, some of the recent systems, some of the recent developments that we have had, you know, using heterogeneous catalysts for the production of renewable chemicals. So with that, I think I already made a very good summary of that, although sometimes I like to start by doing a quick pictorial representation of my pathway. I was born in Mexico City. From there, I moved to UPenn for my undergrad, and there I met my wife, and together, you know, we looked for grad school in this classic two-body problem. We ended up in the University of Wisconsin in Madison, where I worked with Jim Domestic. And by the end of that time, my son Max was born there. From there, we moved to Caltech to work with Mark Davis, working on zeolite chemistry, and our second son, Dante, was born there. And then we moved to MIT, where I started in 2010 over there, and our third son, Dante, was born there. You can imagine I'm seeking with everything I have tenure because I cannot afford to move one more time. This is our no vacation zone as well, just to be safe. Anyway, I'm sorry. In a more serious note, my group is experimental in nature mostly. We work a lot with catalyst design, so we do a lot of synthesis, but we do all the reaction engineering aspect as well, you know, looking at kinetics as well and different types of materials. And our focus, there's a big focus on porous materials, on zeolite, so we work with oxides and transition metal particles as well. And most of the efforts are on biomass conversion, on oxygenate conversion, although we started doing a little bit of electrochemistry and CH bond activation as well. And to summarize just some of the thrust in my group, you know, we started looking a little bit on what we call catalytic cooperativity, you know, on what Lewis acid pairs or Lewis acid-Lewis base pairs can do in activating specific target molecules. We have a big effort actually funded by BP on HDO chemistry for pyrolysis oil. We started looking at transition metal carbides for different types of systems, and a little bit on zeolite chemistry for CH bond activation. But before we go into this, you know, today I'll focus mostly on these two projects over here. I wanted to share with you kind of like the view of how we think about this kind of problems on oxygenate in our lab, why we think it's important, some of the challenges in heterogeneous catalysis, and that will set up the frame on how to why we want to investigate these two particular topics over here. And before that, you know, we spoke about this morning a little bit. I think something that is felt in the entire biomass community is the impact of shale gas, right? And the increasing production, especially in the United States, of natural gas, which has a lot of different consequences, right? And a lot of it has to do with a decrease or a decoupling between the price of oil and the price of gas. And, you know, the United States potentially becoming a net exporter of methane, right? And that, you know, has a lot of different things that will change based on this. And what you notice is that, of course, this can potentially pose a threat for biofuel production, right? Or all the arguments that you typically see in publications where, you know, we want energy independence, we want something that will be domestic. all of these things, in a way are solved by methane. But something that methane will not do, is perhaps it will be more difficult to assemble more complex molecules, more complex oxygenates and building blocks. It will change the distribution of current platforms, and we'll see that in the next slide. And also, it doesn't address the problem of greenhouse gas emissions, right? So I think that is something that we have to keep in mind. And even though this will and is a game changer in the short and medium term, we still want to also put it in context for what it means for biomass conversion. And there's a very interesting article coming from the Weykusen group in the Netherlands. This is a perspective in Angewandte Chemie that recently came out. And where actually it's portrayed very nicely, what the impact of natural gas will be on biofuels, and how instead of looking at it as a threat, it actually can be an advantage. It's on how we can now use biomass as a gateway to come in or bring in the first wave of renewable chemicals, based on the fact that some of these, building blocks will change based on what you will come out of a cracker, usually out of a naphtha cracker. In addition to ethylene, you will produce butadiene, you produce BTX. But once you start feeding some of these lighter alkanes, all of it will change, and you will start producing much lower amounts of this. And that's partially attributed to why we have seen such a high increase in price of something like butadiene in the recent past, for example. And that's where biomass can come in and perhaps be the gateway for this making this first set of chemicals, and then many more after that. And I think that is there's some very interesting arguments in these papers. If you get a chance, make sure to read it. I think it was pretty good. But from that point of view, we look at it from my lab that biomass actually can be very good as a platform for renewable chemicals. It has high oxygen functionality that we can remove, hopefully selectively, and we can start assembling much more complex molecules that would be difficult to assemble either from petrochemicals or from natural gas. And in that respect, there's a lot of things changing in our society. There's a lot of needs for these new types of materials. And I just portrayed here a couple examples, the increasing consumer and regulatory demand for sustainable technologies, like Coca-Cola, for example, having a huge drive to create these green bottles, or bottles that are made of renewable plastic, green building processes, carbon markets, and so forth. We have an ubiquitous use of displays, right? So just, riding in the BART yesterday after arriving at the airport, and you look around and everybody, but I mean, when I looked at everybody in the train, they were all looking at a screen, and I think that is something that has really changed in the last 5 years. And we will need to develop, more sustainable materials for this market, and especially, replace critical materials in these components. We have, an aging population. We have an average lifetime that will start increasing. We'll have new demands for materials and medical science, new prosthetics and drug therapies, preventative wellness products. And as well, with an increase in population, right, we need perhaps new materials for advanced construction, right? And this has to do with adhesives, waterproofing, insulation, coatings, and so forth. All of this will increase in demand, and I think it's a good opportunity for biomass to come in, as well as in the transportation fleet, right? Come up with new high-performance materials and perhaps new renewable sources of fuel, such as jet fuel. So those are some of the motivations that we base our research on, and then we go on into looking at some of the challenges of why we need to develop these heterogeneous catalytic technologies to do so. And of course, one of the first challenges that we observe is the high prevalence of oxygen, right, in this lignocellulosic biomass. And for this audience, I don't need to explain what that entails for the physical-chemical properties, but what we do know is that we need a completely different set of conditions to process these materials, right? So when you look at one of these plots for having oxygen to carbon ratio versus hydrogen to carbon ratio over here, we know that most hydrocarbons are usually located over here. Biomass, of course, has a very high oxygen to carbon ratio, and usually we want to do HDO processes or remove some of this oxygen selectively to come in and be more in this regime over here. And when we do that, we need to use very different conditions, right, than the ones that we're used for in petrochemical chemistry. And most of the times we have to use condensed phases. A lot of times we have to operate in aqueous phase conditions or in the presence of water vapor, which also changes the properties quite a bit of our catalysts. In addition to that, if we want to deploy now these bio-based systems or heterogeneous catalytic systems, our biomass is always hydrogen poor, right? So regardless of the transformation that we do, we have to inject hydrogen atoms one way or another, and to do so, we need to work on redox-active chemistry. And of course, late transition metals are very good. They're usually more expensive, and we want to move away from those into more perhaps earth-abundant materials such as copper, iron, and so forth. But what happens there is that under these aqueous phase conditions, these materials are very unstable and they leach out. So we want to develop new technologies to avoid this irreversible sintering, for example, or agglomeration or leaching. And that's actually a very big challenge in this area as well. And in addition to that, try to develop new ways of or catalytic schemes that perhaps can reduce the number of unit operations. So looking at the entire processes, right? Separation, purification are some of the steps that require the most amount of energy expenditure when we work with some of these materials or these systems. So what we want to do, perhaps replace more homogeneous catalysts with heterogeneous materials and develop these schemes that couple multiple reactions and perhaps, kick out our products or separate spontaneously from water so that we can avoid as much as possible costly separations. And that's something that, especially these last two points, number 3 and number 4, are things that we really think about when we start to deploy new technologies or things that we want to investigate in my lab. So as I told you before, I'll go briefly through some of the recent results that we have had on these tandem reactions with Lewis acids and some of the chemistry that we're pursuing with metal oxides for hydrodeoxygenation of pyrolysis bio-oil. So starting with the Lewis acids, we work a lot with porous materials, with zeolites in particular, and in addition, with the classic uses of zeolites as very strong shape-selective Bronsted acids. We find that you actually can have a lot of nice control, a lot of nice properties with these porous materials in terms of potential for having multi-site arrangement, some confinement effects for directing specific transition states. You can have cage effects, just trying to enter part of a molecule in the cage, and depending on the heteroatom incorporation, concentration, and composition in there in your pores, you have a certain degree of control over hydrophobicity. So all these things are a great platform for catalyst design. And that's when, we look at, in the context of oxygenate transformation, we want to have something that is tunable, water tolerant, that is highly selective, and that is stable, of course. And that's aspect number 1. Aspect number 2 is that when you start looking at some of the molecules that you typically observe from biomass, you see a lot of carbonyl and hydroxyl functionality, right? You always have these two functional groups prevalent in there, and you want to find catalysts that will be able to activate these functional groups. And this is something that usually we don't find in hydrocarbons. And that's when we turn into to Lewis acids, right? So Lewis acids are great at accepting, these lone pairs of electrons from, for example, oxygen in a carbonyl group. And by complexing there, you can start activating the molecules toward different types of transformations. And this is, well known in homogeneous chemistry on how to do, different types of carbon-carbon coupling or hydrogen transfer, oxo transfer reactions. And we have a lot of flexibility, or we have a lot of knowledge in the homogeneous Lewis acid chemistry literature on how to perform some of these transformations. But one of the biggest effects that we have, or consequences of working in this, is that we mostly have to work under anhydrous conditions. And the reason is that water is an excellent Lewis base and actually complexes very strongly with Lewis acids, right? And then you quench them and they become inaccessible for catalysis. In addition, for some of these salts, for example, this is a very simplistic way of looking at this decomposition of something like aluminum chloride. You can then irreversibly transform your salts into hydroxides and oxides, and again, they lose quite a bit of their Lewis acidity in this respect. One of the big exceptions is, for instance, this metal triplets or the lanthanide from the lanthanide series, and these are materials, these are salts that actually can withstand aqueous conditions very well, and they maintain the Lewis acidity even in the presence of water. And without going too much into the details of why is the case for these particular salts, this paper by Kobayashi, he worked a lot on these triplet salts and tried to understand why they were able to withstand this water. There's a lot of different effects. One of the most important ones is what is called this work coefficient, or water exchange ratio coefficient. And it's pretty much a measure of how quickly water comes in and out of the coordination shell around these Lewis acids. And what they found is that as long as this exchange rate was very fast for a particular metal, the metal would be able to withstand Lewis, or would able to maintain activity even in the presence of water, which means that they are able, to bring in carbonyl functional groups or oxygenates or different electron-bearing functional groups into the sphere of the metal. So looking into those particular parameters, we're very interested in looking at now metal centers embedded in a zeolite that has a hydrophobic pore to start activating some of these groups. So for example here, isolated heteroatoms such as titanium, zirconium, tin, or hafnium don't impart a charge imbalance into the framework, such as a trivalent metal would be, like aluminum in a zeolite, so you don't have any Bronsted acidity in there. But they have open coordination sites, so you will be able to accept pairs of electrons, so these will effectively act as Lewis acids. Now the important thing is that water doesn't have to coordinate very strongly in such a way that it will quench the Lewis acidity, and that's where slightly, this hydrophobic pore comes into play into alleviating some of this very strong coordination to the metal center. So we take a look at some of these materials, and these are materials that have been described in literature before. So Avelino Corma was the person in Spain who pioneered some of this chemistry, and he found that some of these zeolites containing, for example, tin or zirconium, were very active hydrogen transfer catalysts. So for this reaction, what is called the MPV reaction, it's a way of changing functionality from a carbonyl to a hydroxyl. So you pretty much have these two molecules, and they flip functionalities by doing this transition complex around this active site that can accept two sets of oxygen atoms in there. So you can see over here what you have then is an intramolecular hydride shift. So you shuttle pretty much hydrides between molecules. But that is something that can be exploited many different ways. So some of the work that we did in Caltech, working with sugars, was to exploit this feature of Lewis acids to start shuttling hydrides between intramolecularly within the same molecule. And you can see that, for example, glucose can undergo an intramolecular hydride shift and isomerize into fructose this way, rather than doing a classic proton abstraction chemistry as you would do with a base catalyst. And something that we have found as well, something that is very interesting, and I will not talk too much about that today, is that in the presence of borate salts, you can start changing how this sugar is actually complex to the active site, and instead of having hydride shift, you can have carbon shifts. You actually break carbon-carbon bonds within the sugar and rearrange them in such a way that you have what is called this intramolecular hydride shift. If you're interested in this chemistry, there's a couple of papers that we have published showing the details on this, but that is something that is actually quite fascinating in the realm of hydrocarbon chemistry, of breaking and rearranging carbon-carbon bonds at low temperatures. But what I wanted to do today is show you, some of the other strategies that you can follow in performing, exploiting some of these properties of hydrogen transfer chemistry of Lewis acids to perform tandem reactions. So one of the first reactions that we targeted is the production of GVL, or gamma valerolactone. So this is a molecule that has raised quite a bit of excitement lately, mostly because you can use it as a fuel additive, or you can use it as a co-monomer to do certain kinds of polyesters. And as well, you can use it as a green solvent. It's one of the handful of solvents that can actually dissolve carbohydrates. And that's why, it has obtained quite a bit of attention in the recent past. The way to produce GVL, or the way it has been popularized, starting from cellulose or hemicellulose, you transform the sugars in them into levulinic acids through a classic Bronsted acid catalyzed system. And what you do then is just with classic, palladium or ruthenium chemistry, you hydrogenate this carbonyl group into a hydroxyl group, and then you create what is called a hydroxypentanoate. Because of the distance, you have 4 carbons in between the carbonyl group and this hydroxyl group. It spontaneously lactonizes, and that's how you form GVL. And usually, the process is limited by this step over here, where the yields are about 55 to 60%, and this is actually quantitative, but requires the use of precious metals in there. So what we wanted to ask, is there a way for us to produce GVL, perhaps without the use of molecular hydrogen or precious metals? And as you can imagine, what we want to exploit then is the ability of these Lewis acids to do transfer hydrogenation chemistry. So imagine a process where we start from xylose to produce furfural. There's a lot of well-established methods on produced furfural in high yields from xylose. And you usually use a Bronsted acid catalyst for this step. You can perform then a Lewis acid transfer hydrogenation step where you convert your furfural into furfural alcohol using a sacrificial donor, and we will talk about what we do with this product in a little bit. But you perform a hydrogenation, transfer hydrogenation chemistry where you transform your furfural into furfural alcohol. This can then undergo esterification chemistry also in the Lewis acid site. You can then open up the ring with a Bronsted acid catalyst to make a levulinate derivative. And from there, you can imagine you can do a second transfer hydrogenation step where you create the pentanoate, and that will spontaneously lactonize to GVL. So that was our thinking of how we could couple perhaps a Bronsted and Lewis acid catalyst to go all the way from our sugar to our GVL without using molecular hydrogen or high pressures to molecular hydrogen. So the very first thing that we did, we just wanted to look at the proof of concept. We started screening catalysts in a batch system. So for example, a catalyst containing zirconium, such as zirconium beta, is very active in this particular step, taking levulinate acid or methyl levulinate or butyl levulinate in the presence of a secondary alcohol or a primary alcohol. Actually, a lot of different alcohols work for this step and produce GVL. Production rates are good, but for this particular step of methyl levulinate to GVL, they're much lower than for the initial step, furfural to furfural alcohol, which I'm not showing here. But what I want you to remember is that our zirconium beta appears to be the most active catalyst for this transformation. Usually the way we operate, we always do a lot of reactions in batch, and then we move to our flow systems to look a little bit more detail at the stability of the catalyst, at the kinetics. In this case, for example, we run at 60% conversion in a flow system, make sure that our catalyst doesn't deactivate for this transfer hydrogenation step, and from there we move into the coupling. For example, what can we do now that we have our furfural alcohol and we know that we can produce these levulinate derivatives or convert them into GVL? We wanted to start coupling this with our Bronsted acid step where we open this up. And this actually is not a trivial reaction. Making these levulinate derivatives either in water or in an alcoholic solvent creates a lot of byproducts, and a lot of it are consecutive reactions. And what we found is that usually you want to operate with a strong Bronsted acid, but you need something that has a good stability and open architecture, and that's when we went to our what I call this molecular engineering toolkit, and try to create these zeolites, and this is mimicking the work, for example, by Ryu in Korea, where you can start making some of these zeolite nanosheets, which are, I hope you can see them from far back, where you have pretty much a unit cell-wide DSM-5 catalyst that has a lot of open sites with still quite a bit of strong Bronsted acidity. So with that, we're able to use both catalysts simultaneously and either in flow mode, or in this case I'm showing the batch reaction data. We're able to obtain GVL starting from furfural with very high yields without using these precious metals or molecular hydrogen. And we actually show that even starting from the carbohydrates, from hemicellulose or xylose, you can still obtain very high yields, not as high as 80%, but you're in the low 70s in that respect. But for us, what is exciting is that this offers a potential platform to start transferring hydrogen amongst molecules in your biorefining scheme. And as I told you, these secondary alcohols are used as sacrificial hydrogen donors, but they become ketones. And we know a lot of very good chemistry that you can produce now with these ketones for carbon-carbon coupling, or you can now use them as hydrogen acceptors in a different step. For example, I'm not showing this here, but we have seen that starting with something like 1,4-butanediol, you can do this exact same chemistry of hydrogen transfer into your butanone and then produce something like butyrolactone and regenerate your butanol solvent. So there's a lot of different creative ways that you can start thinking of how to transfer hydrides between atoms using this type of chemistry, which could be very powerful. And then, we're looking at other ways of applying this same approach, of hydrogen transfer. And one of them has to do with now coupling transfer hydrogenation and esterification reactions. And this has to do, for example, starting with something like HMF, and starting to create some of these ethers that have been found to be good diesel or blending components. And we just spoke a little bit with Alex Bell on this chemistry because, just trust me that the heating value of these molecules is good. There's preliminary tests that show that it actually can be good blending agents in gasoline. But the Professor Bell's group was probably the first one to show that you can actually couple these steps, starting from HMF. We know with Bronsted acid chemistry that you can do an esterification reaction with the hydroxyl group over there very easily. But you always, if you want to make the diether, which is a preferable ether component as a fuel additive, you would have to hydrogenate then this carbonyl group into an alcohol and then do the esterification. That's where you have to couple, for example, a platinum-based catalyst with acidic resin, for example. And you can imagine that a very similar scenario as what I showed you for GVL can be applied for this exact same process, where we can use transfer hydrogenation chemistry to create a dialcohol over here, and then either use the same Lewis acid that we have or couple it with a Bronsted acid to do the diether synthesis over here. So a schematic representation of how the network might look would be something like this. Our starting material is HMF. Our target product is what we would call this BEMF, or bis-ethoxymethylfurfural. And you can see that you can go through this route over here where you do the hydrogenation and then esterification. You can have this other pathway where you do a first esterification over here on the hydroxyl group and then do a hydrogen transfer followed by esterification. Or you can go through this acetal route where you create acetals and go back and forth. It's a reversible reaction, and perhaps land here. We know now that actually this pathway is very unfavorable, and usually you go back through here. But what I wanted to show you is, again, we can now couple this with an alcohol, a primary alcohol, a secondary alcohol, and do this transfer hydrogenation chemistry and start coupling these two steps over here. So again, similar methodology. We do the screening with our materials. In this case, we actually resorted, based on some of the properties of zirconium beta, we resorted on actually making a new zeolite called hafnium beta, so incorporating hafnium into the framework of the material. Hafnium has very interesting properties, actually very similar to zirconium, but a little bit stronger Lewis acidity, and we can discuss that after the talk if you'd like. But what we find is that actually hafnium beta in our initial batch screening is a very good catalyst for producing, doing the hydrogen transfer step and the hydrogenation chemistry as well. And a classic batch-based time profile would look something like this. And this is something that happens very, very commonly in this field, is that many times we stop at this, we would do a second regeneration or a second test in a batch system without really studying kind of like the long impact in a flow system. And something that we've been trying to do is now, after doing our screening in a batch reactor, we always switch to a flow system to really look at the dynamics and what happens to the active site with time on stream, which I think is something that is missing in a lot of the studies sometimes in heterogeneous catalysis. And what we find actually is there's some very interesting properties over here, and I'll just show you a snapshot of what we see, and we have coupled this with a lot of characterization studies of what happens to the active site. But for hafnium, we see this very interesting profile over here on the chemistry. We see this kind of like two steady state regimes with these two initial deactivation profiles. We see that we produce quite a bit of acetal, and after our second, this deactivation step, we actually changed the product distribution quite drastically, and instead of producing our esterification products, we continuously produce our dialcohol products over here. If we switch to our tin catalyst, we see that even though it's a little bit slower for the esterification of HMF with ethanol, it's more active and, I mean, not more active, it's a little bit more stable, still producing, though, quite a bit of acetal byproducts and deactivating very slowly over here with respect to the diether. Now, when we switch to, for example, 2-butanols or alcohol, suddenly we see almost quantitative yields of our diether over long periods of time, in this case with our tin beta. For example, you see this initial deactivation and then followed by a steady state conversion over here where we don't see any acetal products and we see almost exclusively the diether product. And this is something that we're trying to investigate. What is the difference when we do this esterification with ethanol versus butanol? We still create water. We create a little bit less water with the butanol system because we are not creating the acetals, but water has a huge impact on the catalyst itself. It is not leaching. It doesn't make the catalyst leach, but it actually changes the local environment around the tin site. We see, these double hydrolyzed sites, and this is still work in progress, but we're starting to see very interesting effects of water in this long-term long-term studies on the active side as well, even though we are not leaching the metal out of the framework over there. And we have a lot of questions, reminding there of what is happening over here. What is the impact of water? What is the absorption profiles on the active side? What is causing this deactivation? And we know it's not coke formation because our MPV step, or transfer hydrogenation step, remains active. So we have a lot of potential questions of what is happening over here, what is the mechanism, but there's limited ways in which we can really probe the structure, we can probe the active site. And that's where I wanted to share with you, some of this, we've been doing a lot of NMR methods or techniques to try to investigate what happens around this active site. And this stems from the fact, of going back to the basic as to what determines, the reactivity of some of these materials. We have, to synthesize the zeolite in a fluoride media, and that ensures that we have no pore defects over there, so we have a very hydrophobic pore. And different heteroatoms, will have different types of reactivity. So, coupling this hydrophobicity with the type of metal that you will have there really impacts reactivity and the stability of the catalyst. And there's a lot of different other factors that contribute to reactivity. We see very strong solvent effects. We see very strong heteroatom effects, and there has to be very specific interaction between this Lewis acid and the substrate. For example, in Korma's work, it has seen that for these MPV steps, just changing, from cyclohexanone reactant to benzaldehyde completely changes the activity if you use tin beta or zirconium beta under exactly identical conditions. So, there's a lot of questions as to what is happening there around the active site, and that is something that we want to probe a little bit more with NMR. And, we know that if we impact, how these molecules actually react and absorb on these sites, we should be able to have a better handle on the product distribution. So we relied on methods such as readout techniques. These are called rotational echo double resonance techniques, and this has to do with establishing a very kind of clever pulse sequence, to eliminate and then reintroduce dipolar coupling or dipolar interactions in the particular nuclei that you want to investigate. And by doing this pulse sequence that introduces in a very systematic manner this dipolar interaction, you can start measuring distances between the two nuclei over here. So in this respect, for example, we can measure with these reader experiments very well, the distances between specific carbons when we label our sugars or we label our reactants with for example, the tin center. So we know how far away these ones are, what is in close proximity and what is not to the active site, and we can start piecing together more or less under conditions we can heat this up under reaction conditions, what is happening dynamically around the active site. Of course, when we do these types of experiments, they are actually very elaborate. They're very time-consuming, and we are very fortunate that we have this center called the Francis Bader Magnet Lab, where we can perform a lot of these solid-state NMR experiments for long periods of time. For example, to collect this graph over here that I'm showing you, this took about 240 hours of NMR time. And you can imagine that this is extremely, extremely expensive to do unless you have some buddy like Bob Griffin in my case that allows you to use these machines for a while. So this is 10 days of straight NMR time in a 700 megahertz machine. So this is a lot, and that's when we start looking at that. NMR is a very powerful technique, and we start looking at what else can we do to decrease these acquisition times. Something that we have been exploring also with Bob Griffin is the application of what is called this hyperpolarization techniques, such as dynamic nuclear polarization, or DNP. And for those of you unfamiliar with NMR, or if you, for instance, are familiar with a technique such as CP or cross-polarization, you can think of DNP as a cross-polarization on steroids. Something that you take microwaves, you have a biradical, such as this one over here, you polarize it with microwaves, and then this polarization actually can get transferred to the nuclear of choice, or to a solvent that has protons, and then you can transfer, this polarization back and forth, and you can enhance the signal in your NMR quite a bit, reducing acquisition times by a lot. So, for example, we use it to understand what happens inside of the pores of these zeolites when sugars are in there. You can do these 2D experiments, things that would take a ridiculous amount of time to get. In this particular signal-to-noise ratios, for example, we can get in about 10 hours using DNP. And with this, we have discovered that, for example, sugars inside of the pores of these zeolites actually exist in the furanose form. For example, glucose in the furanose form is very rare in aqueous solvents, right? We have a very, very small proportion of that, but somehow inside of the zeolite, with these 2D experiments, we're able to confirm that it actually exists in the furanose form, and we don't quite understand why it's the case. So this is something that we continue to investigate. And another big issue is, as I told you, this framework incorporation of tin centers is very critical for us to understand reactivity. And a big bottleneck in investigating these materials with NMR is that if you want to do tin NMR, you have to enrich the sample. You always have to buy an enriched precursor like tin chloride. And the last quote that we got, for example, for Cambridge Isotope was for a gram of this tin chloride, you have to pay about $12,000. And it's extremely expensive to do. And it really limits, because it really limits your ability to perform your NMR experiments and really figure out what is happening over there. And so something that now we have developed is you can create these DNP techniques. You can implement these DNP techniques to probe your active site in a hydrated state or a dehydrated state without enriching your material. So you can actually do your DNP, and in a matter of about 20 to 17 hours, you can obtain a spectrum that is beautiful without enriching the sample, and really allows you to now establish some of these reader techniques, for example, that I was telling you about, without having to use too much time. And we're very excited because you can see, for example, this image over here. This is running also for almost 10 days, our 119 tin sample with natural abundance, without enriching, and we didn't see a signal at all. So we believe that this actually will help the catalysis community start using NMR a bit more to probe the active sites in these materials. And with that, I'd like to shift briefly to share with you some of the results that we have had on using reducible metal oxides for HDO chemistry. So this is different from the zeolite chemistry I just showed you. But the reason we're interested in this, and this is something that BP has asked us to look into, is that, looking at the classic pathways for biomass conversion, we look at this middle range temperature conversion pathway where you take biomass, heat it very quickly in the absence of oxygen, and pretty much liquefy it. So you produce some condensable gases, you produce some char, and then you produce what is called this bio-oil, or this soup of components that are in the liquid phase. And the challenge that we have is, how do we establish a heterogeneous catalysis scheme that will be able to deoxygenate these bio-oils and transform it into molecules that are more easily integrated with current refinery streams. So from there, you can imagine that you would want sort of a dream catalyst that would do a deep deoxygenation, kick out your oxygen as the only three ways possible, CO2, CO, or hydrogen. You want to minimize your hydrogen consumption, minimize carbon loss, or at least keep the carbon chain length of your starting molecules, if not increase it. have high stability and recyclability, of course, low cost as well. And this is obviously a dream list because we would all like to have catalysts all the time that are like this, but it's very rare actually to find them. Whoa, I didn't know I had that animation there. But so just to give you an idea of bio-oil, right? So you have your wood chips, for example, here. You pyrolyze them through these very simple, downflow or upflow reactors. You liquefy it, you get this bio-oil, and what you have is this family of components, right? You have short oxygenates, you have furanics, phenolics, and a whole bunch of different materials over here. You have a lot of water still in there, and you have a lot of organic acids that are corrosive. So that's why you cannot keep bio-oil for a long time because it just starts polymerizing. So one of the big challenges is, how do you stabilize it? How you do this first deoxygenation path so that you can do something useful with this bio-oil. So the concept that we're pursuing is what the guys at NREL actually call ex situ catalytic pyrolysis. So this is a depiction of a reactor. So you have your biomass over here. You feed it in this downflow reactor, or in this case, this is an auger reactor. So you actually, feed it over here through a twin screw extruder that is heated, and you kick out the bio-oil as a vapor over here that you eventually quench and separate over there from the solids. So the question here is, can we intercept the vapors here before quenching? While they are hot and you are working at temperatures of about 300 to 450 degrees C, can we work in this temperature regime to do some of this HDO chemistry before we quench it? I'm sorry about this. I didn't know I had this animation. And the idea would be then, rather than following the classic approach, right, of doing first a condensation, increase your chain length by taking advantage of your molecular handles, and then doing your HDO and hydrogenation chemistry to get your final hydrocarbons, what we want to do then is do our HDO chemistry first over here, and then do, by producing aromatic phenolphins, do our known oligomerization chemistry to end up with this type of hydrocarbons over here that we can perhaps, mix with the refinery. So of course, the question is, what catalyst would you want to use that would take any of these materials and perhaps convert them into a mixture like this? And that is not an easy question to answer, right? Because there's a lot of different cross reactions that you will have. The other thing is that perhaps not only you would want to deoxygenate, but perhaps they're looking at a catalyst that can perform some of these carbon-carbon bond forming reactions, right? So looking at lignin, you will have a lot of ether groups over here like this that are difficult to break, but once you break them, it actually would be very useful to have some kind of molecules like this that would have some interesting fuel properties over there. So can we find a catalyst that would be able to do that as well? So our inspiration came from a couple different papers, but our original thought that we know now that it's a little bit different. But when we first started this project, we started looking at metal oxides that have been used for oxidation chemistry, right? Through this classic Mars-Van Crevelen mechanism, where you actually use oxygen in the lattice of your oxide to perform the oxidation chemistry. In this case, we would want to operate in reverse, where we create oxygen vacancies on our oxide, and then let the oxygenate land on the surface, and then use hydrogen to do a hydrogenolysis reaction over there, and then regenerate again that vacancy with hydrogen again. So it would be kind of like a stepwise dehydration reaction. So, we did an initial screening with different types of oxidation-based catalysts, right? So we have molybdenum, vanadium, iron, and from there we see that actually molybdenum gave us some very interesting results for acetone HDO chemistry. So we actually produced quite a bit of propylene, and then we saw hexenes that came from the HDO of the coupling product of acetone, for example, methyl oxide in this case. The rates were good. All the other catalysts also worked, but not as well as molybdenum oxide. So we started, doing, again, our classic approach, a quick screening over here of different molecules. And what we found is that our selectivity to hydrocarbons was always very high with molybdenum oxide, working at hydrogen pressures of less than 1 atmosphere, right? So we would work under atmospheric conditions, low partial pressures of the oxygenate. And what we found very interesting is that the bonds that we were breaking in these molecules were not what we would expect from our bond energy analysis. So looking at, for example, the lignin fraction, you have, these kinds of building blocks always. These are the classic model compounds that people use, in the lab. Things like guaiacol or anisole, they have these methoxy groups and hydroxyl groups over here, and phenol, of course. And when you do, the bond energy analysis, start looking at what are the strongest bonds. Over here, you see that, let me see if I have it over here, this methoxy bond over here is the weakest, this aliphatic bond, and then the aromatic one is the stronger, and of course the phenolic bond is the strongest of them all, So what you would want to do, or what you would expect when you perform some of this HDO chemistry would be to always cleave this bond first, followed by the rest. So in the interest of time, I'm going to skip this, but what we find, right, is when we, go to differential conditions in our reactor, we actually see a mixture of, aromatics such as benzene, and then we see phenol in about a 1-to-1 proportion. So when you go to 0% conversion, this changes a little bit. But we found it very interesting that even though we should expect a lot of phenol production in the beginning, we actually saw quite a bit of benzene and toluene and xylene actually from actually alkylating this process as well, these molecules as well. So we started looking a little bit more about, what could be happening. We started looking at what is going on at the surface. So this is a very simplistic depiction of what we think is happening. We started looking at the rates and the bond enthalpies. We knew that these oxygen vacancies are important. In this case, we're plotting the bond enthalpy as a function of our observed rate, and we see one of these classic, volcano relationships with molybdenum oxide at the top over here. So we knew, somehow these vacancies are important in the catalytic cycle. But we also know that hydrogen actually is quite important. For instance, if you turn hydrogen off, the reactivity immediately decreases. You turn it back on, and it's as if you had never turned it off, except that it deactivates a little bit quicker. We see from our order studies, a half-order dependence of hydrogen. This suggests that we have this dissociative adsorption on one side, but we also see zero-order dependence at all different types of conditions on the oxygenate. So what we start seeing is that perhaps we actually have two catalytic sites over here, one responsible for the hydrogen dissociation, one responsible for oxygenate adsorption, and we're still trying to deconvolute what is going on with this particular surface. Something that was very intriguing to us is that, you look at these rates, imagine the number is close to 100, and it's, in this case, just remember the number 100. But when, if our catalytic system, if vacancy creation by reducing with hydrogen is actually involved in our rate determining step, so kicking out this oxygen from here should be very relevant, right, in our mechanism over here. But when we look at the transition, from molybdenum trioxide to molybdenum dioxide, when we look at the reduction of that, it actually is slow under this condition. So we know that there's something else going on. This vacancy generation cannot be the only thing explaining the kinetics that we see. So we're still investigating that. In addition to this phenomenon over here, if you operate at 673 Kelvin at 400 C, the deactivation is very drastic. You lower the temperature, and you start seeing this induction period on the catalyst, followed by a much flatter, rate of deactivation. We see that this is the 400, first order deactivation rate, and these are the other ones at a different temperature. And we start asking, what is going on? Why do we have this induction period? What is happening on the surface? We start doing some XRD analysis in situ, at different times in the reaction. These are the X-rays after reaction, and we see that the reactor or the catalyst spent at 400 over here mostly transformed to molybdenum dioxide, which we know that was actually inactive when we did some control experiments. But the other materials have these extra phases in there, and we start investigating what is this extra phase. And when comparing to an oxycarbohydrate, we see that partially carburizing the surface matches the X-ray spectrum. And that's when we started looking at TGAMS, other techniques to try to figure out where is this carbon going. Our carbon balance couldn't quite close all the way, and when we do the calculation, we start seeing that in fact we are carburizing the surface a little bit. And looking at in situ X-ray, we see a very interesting dynamic effect of the surface. where, at 600 we see at 400 degrees C, we see a very quick transformation of our molybdenum trioxide into the dioxide. But when we go to a lower temperature, we see mostly a mixture of the MO2 with this oxycarbohydrate. So now, this is where we're starting to look a little bit more carefully about what is going on. Looking at the XPS, we see that we have this prevalence of this molybdenum +5 species over there, and we're trying to correlate, the presence of this material or the presence of this phase or this state with our reactivity. We know that after deactivation, we can again, oxidize the material to MO3, and then the entire cycle begins. So our current theory right now has to do with the fact of, partially carburizing the surface, have this active molybdenum carbohydrate in there that perhaps allows us to have, some metallic centers that allow dissociation of hydrogen with some vacancies or under-coordinated sites that allow the absorption of oxygenates. And with that, I would like to finish just very quickly with why we think this is important, where our molecular engineering tools can come into play again in light of this talk. And this has to do with, from this path, we have seen that oxycarbohydrates or oxycarbides are important for this HDO chemistry. But independently, we have learned, for example, a group from Aditya Band's group in Minnesota that molycarbide actually does this reaction very well at a slightly lower temperature. From Jingwen Chen's group, something similar. From the Higgs group in Notre Dame with phosphide, something very similar. So we're starting to converge on how these particular materials are actually excellent HDO catalysts that can perform these reactions under low conversion. Under low hydrogen pressures, And so we started looking a little bit more into carbides, and this is something that is a very interesting area of research, but synthesizing carbides is actually quite difficult, and it has to do, depending on the metal that you choose to carburize. For instance, tungsten is difficult to carburize because of the high barriers that you would have in putting the carbon in the lattice. You have this graphitic carbon that would go on the surface. And, we recently developed this very neat technique to actually make very monodispersed tungsten carbide nanoparticles that have excellent activity for this HDO chemistry. And I won't have time to show you some of these results, but what we find is that, when you have this very interesting structure sensitivity effects, when you go to these very small sizes, when you do not have any carbon deposition, you have metal termination, and you have control over the phase and the composition of these carbides themselves. And with that, what I wanted to show you today is, this power of using, multiple sites to do these tandem reactions, how we can now start looking at, multimetallic or oxide chemistry mixed with carbide chemistry to do HDO chemistry, and some of the very neat potentials that we have on catalyst design to keep on promoting this type of reactions. And lastly, there's a very nice perspective written by Stephen Zhu that was published in Nature in 2012. And the very last paragraph had this very nice quote that I found very interesting that says, the Stone Age did not end because we ran out of stones. We transitioned to better solutions. And the same opportunity lies before us with energy efficiency and clean energy. And I think in a center like here, like EBI, we are at the forefront of doing precisely this. And with that, I'd like to acknowledge, of course, my group, Bob Griffin for the NMR, funding agencies, and I'll take any questions you would have. I know that lunch is waiting for everyone after this, but maybe we'll have time for a couple questions for this.
I have a question.
Yes.
So you showed something about making GBL from using osmium, butyl osmium, I guess, is what you had over there as a catalyst.
Hold on. Can you repeat making GBL?
Without using hydrogen.
Correct.
From sugar. And the catalyst, the catalytic system you were using was butyl osmium over there. Is that right?
No, it was zirconium exchanged zeolite beta. So zirconium beta.
So it would be a recyclable catalyst in that case. So you don't see any deactivation on that catalyst.
Correct. Yeah. So when we operate in the flow reactor, we see, well, we only ran for 40 or for 50 hours, and we saw, negligible deactivation for that. And this is, it's a heterogeneous gas. Yeah.
It's not OSBU, I thought it was hospital-butyrate or something like that.
OBU, what's the butyl group? Just butyl group, because we were working with butanol.
OS meant what? Oh, this is oxygen.
Oh, oxygen sec-butyl. I'm sorry. Maybe
that's what it was.
That is the R group. I'm sorry. So maybe I should change that. No, that was the R group.
Sec-butyl,
That makes sense.
From the 2-butanol. Yeah, it's the ether product over there. Yeah.
Now we got it.
Yes.
So you mentioned that you have a little degradation in the case of molybdenum trioxide.
Correct.
Because of overreduction to molybdenum dioxide.
Yep.
So if you turn down the hydrogen pressure from, let's say, 5 kPa, could you prevent deactivation that way?
It slows down. It still deactivates because when you look at the phase diagram on what are the reduction temperatures for moly trioxide, it's the regime is there in between 340 and 350 when you start switching from MO3 to MO2. So you can turn down the pressure a little bit, and it will slow down a little bit this reduction, but it will happen inevitably. Something that you can do and that actually works quite well is you can alloy your molybdenum with something like titanium, for example, and there's a lot of work out there that shows of how you can start modifying these reduction profiles of molybdenum by alloying with another heteroatom. Yes.
So in your first part of talk, so what is the comment on using the primary alcohols as sacrificial donors for hydrogen usage?
Correct. So the motivation would be that things like 1-butanol or 1-ethanol should be readily accessible in your biorefinery. So perhaps even though we will not be able to get away from an external hydrogen source, the reason this could be exciting is that you don't need to rely on molecular hydrogen to do some of these transformations. So when you start recycling your solvent that will have a mixture of butanol and butanone, the oxidized product, you can now couple that solvent. You can use that solvent in a different step for a different transfer hydrogenation, and perhaps regenerate your solvent and create some other transformation where you remove hydrogens from, like this case of the 1,4-butanediol into butyrolactone. So that is the motivation in there. So these alcohols we should be able to have in a biorefinery readily available. So we can use them as sources of hydrogen. Or if you want to do coupling chemistry with those ketones, there's a lot of chemistry available to do that as well. Yeah.
There are no other questions. Let's thank Yuri again.